Okay, hi everyone. So today we'll look at paper two exam practice. In terms of content, let's say that it's not as much content heavy, okay, as the other papers you've done so far. In sense that, well, as you know, biology is really like a lot of content, a lot of things to remember. Physical chemistry, a lot of different topics coming together, so still quite like content based, like heavy. But organic chemistry, I think, is all based like building up from some basics, right? Of the basics of organic chemistry, which is basics of mechanisms, and of course, a lot of reagents and so on. But that's why we will try to focus a little bit more on the exam practice. We'll try to do a little bit more dynamic revision to cover at least all of the functional groups and all of the mechanisms, interconversion, and so on. Okay, so in terms of practicals, we'll have a look at them because very likely to come up as there are only very few, okay, and it's a good chance to revise specific reactions as well. And then we will look at exam practice, of course, key concept, but we'll go straight into exam questions, okay? So if you need to have a look at the topics, you can have a look at this list, okay? One thing very important to remember that it's easy to forget when you just do organic practice is that the physical chemistry part, it's still in this paper, okay? Which means that we have to expect some calculations here and there. We could have some kind of reaction like acid and base and redox because, as you know, of course, it's very interlinked with some of the functional groups, interconversions, and specific reactions of functional groups. Shapes is very important. As well as electron bonding and structure, and so everything linking to intermolecular forces and so on. Okay, so just be prepared with the mix of questions of these foundation or like the basic of physical chemistry. Okay, what is just AQA exam board that has rate equations in it as well, so like calculation of the rate. But I think this was revised for paper one, so I won't spend time on it. Okay, you know, the papers and the practicals. As you can see, just a few. Test is one important one that sometimes can be tricky to remember, so we will look at the key tests. Synthesis of organic liquid, organic solid. So, sorry, we will revise some of the like the key steps, and qualitative analysis of organic functional group, which is actually the same like the tests. Okay, you know at this point how to revise practicals. Revising the topic first, then using this visual help to really describe all the steps, and then analyze variables, how you manipulate the data, limitations, sources of improvement. But at this point, you know all of it. So to revise a little bit some of the practicals and also to start the revision of the topics, distillation of reaction product, it's an important practical, and not only for that, but you will see many flow charts when you have to for example, find a product or design a conversion. The oxidation of alcohols is a really important one. Okay, so revising very briefly, primary alcohols can be oxidized to aldehydes, can be further oxidized to carboxylic acid. Very important to remember the key definitions: oxidation, loss of hydrogen, gain of oxygen, loss of electrons. Okay, why? Because this tells you what can be oxidized further or not. Because all of the tests that you will see, or the further reactions of aldehydes, they're just oxidations. And why can this be oxidized? Why? The product of the secondary alcohol oxidation, which is the ketone, cannot, or carboxylic acid cannot, because there are no other hydrogen that can be removed. Okay, so observing that, useful to avoid any blackout if you don't remember any reaction of aldehydes and ketones or so on. Okay, basic of oxidation. Also, some kind of question that very often come up is why tertiary alcohol can be oxidized. There is no that hydrogen that can be removed. And then, as you know, the first step of oxidation is always addition of a double bond. So the pi bond between carbon and oxygen, and then there will be the OH attached. Okay, so this is also important because many test tube reactions, so to distinguish between aldehydes and ketones, as I said, that they are oxidation reaction, but also if you have an alcohol, if there is an oxidation reaction, you know that you will have a primary or secondary alcohol and not a tertiary. Okay, so all of these are very important information when you do the full chemical analysis for structure determination. Okay, so distillation, some of the key things, well, actually one very important thing, the oxidizing agents, because those are not just reagents that you need to know to convert functional groups, but now that you revise all the reagent, think about, is there a change in color? Is there an observation that I can make? Because that would also be a chemical test, okay? So potassium permanganate is 1, purple to colorless, and potassium dichromate, orange to green, okay? The reaction involves transition metals. You could be asked to write half equations for that, okay? So, be prepared, because as we know, there is the redox topic could also come up, okay? Just to be prepared. But the colors are important, and the way to remember it is just notice it as you encounter them in your practice this last day, okay? That's it. This is also one of the test tube reaction, all of the colors, if you don't remember, it's a useful one to do the last second revision before you get into the room of the exam. Okay, because we often use our working memory, which lasts just very little time. But if you revise it just before you enter the room, is the thing that would stay in your mind, So if you really struggle remembering something, revise it just before you get into the room. And the colors, it's a very common one, okay, to forget. Anyway, in terms of practical skill, of course, the setup is important. You could also be asked to write the apparatus, both distillation and reflux, okay? Difference, notice in the apparatus, of course, distillation, it has the condenser, condenses out. Reflux is one, it's just one condenser. The water enters and the water out, very important to label it right, okay? All the labels, so notice just the key things of the apparatus, the thermometer and so on. With the reflux, I've seen questions before about little details that is sometimes hard to remember. One could be why of the antidamping granules and why of, and if the reflux apparatus is sealed or closed or opened. Okay, so anti-bumping granules, they're important because avoids the formation of large bubbles, okay, and the spilling of the reagent, okay. The reflux condenser, if you think about it, reflux is the apparatus used always when it's prolonged heating and we don't want open flame, okay, because of course most of the time most organic compounds, they are flammable, right? So we don't want open flames. So that's one safety precaution to consider if you're asked any safety precaution with organic chemistry. And the reflux, normally it's open because we don't want buildup of gases, okay? So normally that's open, okay? Just want to go through these practicals and highlight the very key, the key points that you could be asked. So practicals of organic tests and qualitative analysis of ions, and actually is also the other practicals. So test the tube reactions to distinguish colors of alcohol, aldehydes, alkenes, and carboxylic acid. So I put a little summary here, but I want you to notice that all of these reactions, you know them already. Some of them, you even know the mechanism, you know the type of reactions. The thing is, remember the difference in color, okay? But that's what I'm saying. Notice all of the reactions that you come across. Is there an observation? Because this observation could be the test. So, for example, this first one, what do you think is? So just try to think, what reaction is it? Where have you seen it before? Well, bromine in an aqueous solution. This will be the test, of course, for alkenes, because it's an electrophilic addition. You even know the mechanism for this, okay? And decolorizing bromine water is the test for alkenes, and electrophilic addition is the mechanism, okay? Second test, if you can see the reactions, maybe I will zoom in just a little bit in case it's too small, but I'm focusing on this test tube reaction. Can you notice it? Do you know, have you seen it before? Is a test for a carboxylic acid. Okay, why? Well, it's an acid. You know the basics of acid. Remember, foundation of chemistry will be tested here, and there's basic knowledge for it. carboxylic acid can react with a base. Of course, but we want to have an observation that tells us that an acid is present. And what is that? Well, with a carbonate, releases carbon dioxide. So we would be able to see bubbles. Yeah. And we can also test for carbon dioxide. Okay, so with lime water, you know that this is lime water with form of precipitate calcium carbonate, so it turns milky. Okay, so acid-base reaction to test for carboxylic acid. This one, you know, you should know this test where we have a white, a cream, and a yellow precipitate is a test for halogens. You know this, but of course, this time you need to get the halide because the reaction that we are observing is the precipitation reaction between an halide and the silver ion. In fact, this is done with the addition of silver nitrate. But of course, to get the halide, we need from the organic molecule, we need a reaction. So the first step for this reaction, can you take a moment and see, and if you can notice which mechanism that is? If you notice right, it's a substitution, nucleophilic substitution. In fact, we know hydroxide, it's a strong nucleophile, the most common one we've seen really, but this is the one that nucleophilic substitution of the haloalkane, the alkene is released, and we can test for it. This reaction is very important because if you have a rate, any rate practical or something considering the rate, this is the rate of hydrolysis experiment. Okay, so this is the reaction done. So if you have to design it, and then, you know, you would test for the reactivity of halides, which depends on the bond strength of this because it's nucleophilic substitution. So the bond between the carbon and the halide would break. And how fast the precipitate forms gives us an idea of the rate of reaction. Okay, and therefore the reactivity. But anyway, nothing new. You know, test for halogens, group 7 notes. Okay, then all of these three, they are all the same type of reaction. Can you take a moment and think about which type of reaction is this? In all cases, we have aldehyde to carboxylic acid, alcohol to aldehyde. So what are those? Those are all oxidation reactions, okay? Of course, this is Tollens reagent. The easiest one, I think, to remember for the test specifically only of aldehyde. And well, the observation is caused by the silver precipitate. This is called phthalate solution, which forms the red precipitate with copper. Okay, again, same test for aldehyde, but just remember one. Otherwise, well, the one that is not even a test is a reagent, but it can be used as an observation to distinguish between primary, secondary alcohols or aldehyde, depending, of course, what we're comparing, okay? Orange to green, okay? There is also another one, which is true for DNP. This causes a red precipitate if a carbonyl is present. So this is actually a test only for ketones and aldehydes. Okay, so of course it's limited because then for aldehydes we will need to do another test. Okay, or collect the precipitate of this true for DNP and measure the melting point. The melting point tells us if it's a ketone or an aldehyde. So this is the summary of the test, but you will get a chance to apply to some exam questions very soon. Okay, rate of reaction is the one that I mentioned just before, okay, about the testing the rate of hydrolysis. Okay, so linking to the rate equation, precipitation reaction, the colors, okay? And then you may be asked to discuss why there is a different rate of hydrolysis between different haloalkanes is relative to the bond strength. Why the bond strength? Well, because in the first step, or also called, remember, rate determining step, carbon halogen bond breaks, and that's what determines how fast the reaction is, which means that the weakest covalent bond would be fastest rate. Okay, so everything is interlinked. So notice that the topic of basic of rate of reaction or the advanced topic of rate, as well as the bonding and structure, is all together with the basics of organic chemistry. Okay, now the main practicals for organic chemistry. Preparation of an organic liquid. So in addition to the basic steps of measuring volumes or even masses and chemical reactions, the key part of this, which open questions very likely to come up, is the preparation of organic liquid and separation of them. Okay, so you may recognize that there's which is called the separating funnel. Okay, and if you notice, all the labels here are pretty clear. You have two different densities of liquids. You have a stopcock that you open to separate the two layers. Okay, so the steps, I will read through them just because there are a few key things to notice. 1 second. Okay, now it's moving. So put the distillate of impure product into a separating funnel. So here I'm talking about just the separation method, not the actual preparation of the organic liquid, okay, which is just basic reactivity, but always the basics, volumes and so on, just is the usual practicals, okay? But then for this, distillate of impure product into a separating funnel. Wash by adding either sodium hydrogen carbonate solution, shaking and releasing the pressure for the carbon dioxide produced. So why would we add a sodium hydrogen carbonate? Because these organic reactions often involve acids, and these would neutralize any remaining acid. Of course, but as we know, this produces carbon dioxide. That's why in the shaking, you need to remove the stopper and release the gas, making sure, of course, you don't pour any liquid out. Or you can also add a saturated sodium chloride solution. Why is that? This just helps with the separating the layers, okay? But if you read that in the method, those are the uses, okay? Then you would allow the layers to separate in the funnel and then run and discard the aqueous layer, okay? Or, well, depending which, well, the higher density normally is the aqueous one, okay? Then you would run the organic layer into a clean, dry conical flask and then add the spatula lot of drying agent, okay? So this is normally anhydrous sodium sulfate or calcium chloride, and this dries the organic liquid, okay? Because like separation might not be perfect. So if there is still one drop of the aqueous layer, this would remove it. And then you would decant the liquid into distillation flask, and then you would distill and correct the pure product. So this links back to the distillation practical, okay? So this is the purification for organic liquid, okay? When you have an exam question and you need to identify which is which one is the key steps for like purification, just notice the reaction that you have, like is that a liquid or is it a solid that you produce, okay? There will be some hint in the question. So the key practicals that you may have done, but this also means that you could have, of course, like exam question, you could have mixed like you might have to write a chemical, like a reaction, you might have to do a mechanism before or something down this line, okay? So it's worth to revise this as well. Can you take a minute and notice, tell me, or at least try to identify which reactions of this in terms of name of the mechanism? You can just write it down or thinking, and then I will say it in just a minute. I haven't really mentioned so much like how do we observe and identify mechanisms in chemical reactions. And this will be useful when you do big flow charts, so interconversion between functional groups, and not that you have to design it, but you have to fill up like intermediate or identifying reagent to go from one step to the other. Always observe reactant products and see what has changed. Okay, and this should help you identifying if it's an addition, substitution, elimination. Just observe it. So here we clearly see that the OH has been removed and the chlorine has been added. What is that? It's a substitution. So in fact, this one will be nucleophilic substitution to form a haloalkane. Okay, the second one, what do you notice? The OH is being removed. So alcohol to alkene is an elimination, or also called dehydration. Okay. And the third one, the third reaction that like you might have even done at a school about preparing this liquid is esters. So esterification or condensation, okay? So all of these use the purification technique that we mentioned above, okay? Okay, organic solids. So, sorry, there are no diagrams here, but the key part, we're making a solid. How do we purify a solid? It will be recrystallization, okay? So I want to look at the steps and the reason for it, okay? So let me get the spotlight so you can follow me better. Okay, again, this is all in addition to the very basic of mixing two things and forming crystals, okay? So the typical crystallization reaction, okay? But the recrystallization means that we are forming crystals once again, okay, to purify. So the goal is to remove impurities. So the steps: dissolve the impure compound in a minimum volume of hot, near boiling solvent, okay? The key thing will be the appropriate solvent, okay? So which means that this, you can identify it as is the same solvent as you use in your reaction. So the impurities, when hot, okay, and in the same compound, what it means, like, just basically, sorry, this is a bit too long, but hot, it would dissolve the insoluble impurities, okay? And the minimum volume it's used because like this, we would obtain the saturated solution, and this would enable crystallization and cooling, okay? So not that's why. So to enable crystallization and to remove insoluble impurities. Or soluble impurities, actually, that may, if they're insoluble with hot solvents, more likely to dissolve anyway, okay? Second step, hot filtrate solution, it's passed through the filter paper, okay? This will remove the insoluble impurities, of course, and heat will prevent crystals reforming during filtration. Okay, so this would prevent, so the hot filter is important. That this, it's very common question or very common point that you can discuss if you have like an improvement. Okay, so that's why I'm highlighting these steps. Okay, for improvement, if you have to design it or if you have to discuss this point. So like that, we can minimize the amount of yield that it's lost because insoluble impurities are lost and crystals won't be formed. Then this will be cooled, of course, by inserting bigger in the ice, so crystals will reform. But again, the soluble impurities may remain, okay, because of course it's they would crystallize as well. That's why after the crystals are formed, we will do the suction filtrate. Remember, this is called Bachner flask, which uses vacuum, okay, to separate out the crystals. And the pump would reduce basically it speeds up the filtration, okay, because it uses vacuum. To remove the soluble impurities, would you wash the crystals with distilled water, and then you can dry the crystals between like between just some paper, okay. The problem with this is that normally there is a lot of like a loss of yield because crystals are lost when filtering or washing. Some product could even stay in the solution after recrystallization, or there could be some side reactions occurring, okay? So be prepared to discuss things like yield, and maybe you would have also some calculation of yield if you have an experiment this way, okay? Organic solid, the few experiments that you may have come across, or the chemical reactions that you need to know, or that you also might have to discuss mechanisms, reagents, and so on. One is this one. And guess what this is? Aspirin. Okay. So this, can you notice, can you take a moment to think about which type of reaction is this? Which functional groups are reacting? Take a moment to think about it, to observe it. So we have, this is called anhydride. Okay, remember it's called ethanol anhydride. Yeah, sorry, ethanoic. And remember the name comes from this main chain, ethanoic anhydride. Reacting with a benzene ring substituted with a carboxylic acid and an alcohol. Okay, this is called salicylic acid. The reaction taking place, notice the thing that changes just this alcohol. Now it's an ester. it's the condensation reaction or esterification, because as we know, alcohols can react with carboxylic acid, acid anhydride, or acid chlorides in order to form esters. So one important thing is that acid chlorides are not used, but instead acid, like in this case, ethanoic anhydride, is used because it's cheaper, less corrosive. One thing, if you always use acid, the precaution is it's corrosive. So think about how can you prevent contact with skin, clothes. And it's also less vulnerable to hydrolysis. Okay, that's important. And also less dangerous to use. Okay, can you think about any precautions here? Because it's heated. What did we say about safety, about heating organic compounds? We don't want to open flames. We want to use reflux. Okay, we're still using acid as catalyst, so that's corrosive as well. So we want some precaution with that. Okay, so always think about precaution when we look at these reactions. Okay, so synthesis of aspirin, and this is the second. Can you take a moment to notice which type of reaction this is? This is one very important one to know. It's come up pretty much every paper I've seen. Because it's, of course, benzene. Is nitration of benzene. Okay, notice there is NO2 added. So nitration of benzene, we know we have these two acids reacting together, and it's a neutralization reaction. So this reaction is exothermic. So the acids are kept cool, and the acids are added dropwise to prevent vigorous reactions. Okay. And very important, one particular thing about this practical is that the temperature is always kept very low. And this is to prevent multiple substitution of the nitrogen group on the benzene ring. Okay. Do you remember a little bit the mechanism? First of all, actually, do you remember the name of this mechanism? Can you take a moment and think about it? We see that it's a substitution, even though, remember, when you do skeletal formula, it might be harder to observe it because there is a hydrogen here, right? So this has been substituted. So it's a substitution, and then what did we substitute in? An electrophile. Why? Because the benzene, as we know, it's a nucleophile, electron rich, which means that we will get a, which the mechanism would be electrophilic substitution, okay? Do you remember how the electrophile formed and why the electrophile has to be formed during the reaction? So can you attempt one moment to write down the formation of the electrophile? Try 1 minute and then I'll tell you, I'll write it here. So we have two acids reacting together, but the sulfuric acid, let's do like to revise acid and base, lovely topic for paper 1 and paper 3 as well. This is our, in the conjugate system, this is our acid 1 and this is our base 2. So if this is reacting as an acid, guess what it does? Well, it loses a proton, so it will become SO4 minus. In fact, the HNO3 gains that protons and become the conjugate acid. Remember, the charge is also important. Always think about, is there any charge? Okay, so this would be our base 1 and this would be our acid 2. But this, of course, dissociates more to form our electrophile, which is NO2 plus. And this, as you can see, it has a formal plus charge, which makes it strong enough for the benzene to react. okay? So it's NO2 plus, and then plus water. So this is our electrophile. So this is the reaction to know, very important. But notice that you notice acid and base, conjugate acid and conjugate base, okay? If you have this lovely reaction in the practical, there are other things to consider as well, not only the formation of the nucleophile, the mechanism. Also, let's just focus a little bit on this product. So, why is the nitro in this position and not in the other position? Can you take a moment to think about the reason of the position of this nitro group, which is position 3? So the only position is that one. And remember, it's always determined by the group that it's already present on the benzene. There is a carbon double bond. When there is a carbonyl attached to the benzene ring, this takes electrons towards it. It's an electron withdrawing group. So electron withdrawing group direct at position 3 and position 5. Remember, it's always relative to that functional group, the position. So position 3, position 5, which means that this is only the only place of substitution. Okay. Electron withdrawing, position 3, position 5. How does this affect the reactivity of this benzene? And if you thought about it's less reactive, if you know that it's less reactive, so and the benzene would just be less reactive, sorry, got lost. So it removes electron density to the benzene, okay, which means that it's less reactive, okay? Electron donating group increases their reactivity. Yeah. So those are two strong acids, okay? Which means that the strength of the acid we don't really have a quantitative value to discuss, okay? You know that the sulfuric acid is a stronger acid because how I remember it is that, well, it's a diprotic acid. It has more protons to give away. So it's going to be a stronger acid. So because it's with the two. So I got a question, H2SO4, how do we know that's the stronger acid? Well, because it's a diprotic, so it has more protons, it's more likely to give them away. Otherwise, if we had organic acids, this would be a lot easier to discuss it because we could discuss the Ka values, but those are two strong acids, so we don't really have Ka values, okay? Because they completely dissociate. But we know that sulfuric acid is the strongest acid because it's diprotic, it has 2 protons to donate. Okay? I hope that makes sense. Yeah. Just one more thing I forgot actually about the organic solids. So going back to the practical skills, so to the actual practical steps, the recrystallization, okay, was the important one. Remember all of the key steps in case you're asked to design it, to improve it, or to discuss. And then how do you actually determine the purity if your recrystallization worked or not? Determine purity is done with the melting point, okay? So melting point can be measured in an electronic melting point machine or using a capillary tube strapped in a thermometer immersed in heating oil, okay? So if you see weird diagrams, it's just the apparatus. The important thing is that if impurities are present, the melting point is lowered and the sample will melt over a range of several degrees, okay? That's the other part of purity. Hope that makes sense. Okay, last stretch for the practical is the last one, okay? And we're talking about thin layer chromatography. This is done with the amino acids, okay? When you have a question about amino acid, this can come up. It's very simple, practical. You've done it since year 9, so I'm not going to go over it very much, but there are just a few key things about different, that you've learned before for the amino acids. And for the amino acids, remember that in addition to the usual things, wear plastic, to wear gloves to prevent contamination. The plate is pencil line so it doesn't dissolve in the solvent. The drops on the line have to be tiny because otherwise they would merge. The solvent can't be too deep, it has to be below the line. Solvent front cannot reach the end, otherwise it will just separate in mixtures, okay? Lid, it's used because the solvent normally it's toxic and you want to use it in a fume cupboard, safety things. For the amino acid though, we can't really observe them. It's not like how do you say, like the dyes that are easy to observe. You need to use a UV lamp to spot the amino acids, or using anhydrine, which is sprayed, and this showed purple spots, which are the amino acids. And then guess what analysis we could be asked to do? RF value would determine a specific amino acid. Okay, I'm hoping I'm not going too fast. Now, let's take just a 30 seconds break to, do you have any questions about practicals? So those are the key ones. Is there anything that I understand? Otherwise, I will still show you later some exam questions where, to see the different type of things. So I'll go back to the list of practical. Is there any question about it? 30 seconds. And also, I will take a sip of coffee. Think about it. Okay. No questions? If I'm going too fast, tell me. If I'm going too slow, tell me. If you want to do exam practice and you're bored about explanation, tell me. Okay? For anything, please, it's your practice. It has to be the best for your preparation tomorrow. Okay. Now, for exam practice, the most difficult parts of this paper, I think, is the organic synthesis and organic analysis, because at the end, everything comes together. We will look at a few, of some requests of key mechanisms, but then this is a practice that I would like to do together. So the organic synthesis part, it basically involves interconversion of functional groups, okay? So I'm going to open this a bit bigger, bear with me, because I've put it also in your classroom, all of the reaction pathways. Actually, this is one that I will put later on, but this is the one that I wanted to show you, which is really pretty with colors. And okay, so what you need to be able to do is not only recall the reagents and so on, but this is such a nice way to revise it, because you need to be able to start from a compound and get to another one, okay? And to think about, okay, what's the best reaction pathway that I could design. So for example, so this is a nice way to revise it. So we like you to go through it for literally just reading point by point. Sorry, I'm not sure I'm sharing the red thing. No, I am. Okay, so alkane can be converted into. Okay, so I wanted to look at each of the steps. There are some that you don't really need to know, for example, epoxide, because this is from Compound Interest, okay, which is a super nice website for this type of posters. But it's also looking at the type of reactions. But before you look at the reaction keys, I would like you to practice looking at, okay, if we go from an alkane to an haloalkane, what reaction is taking place? Do I remember the conditions? Okay, so it can be a very active type of recall that you can do with this. Okay, so the key ones that I would like to highlight: alkane to haloalkane. Is it clear for you if I look like this with the spotlight, or is it a bit too overwhelming, too many things on the screen? If so, just say yes on the chat. Otherwise, I'm just going to continue like this, but I want you to have to be clear. If it's clear, don't say anything and I will continue. But if there is nothing, if it's hard to follow, just let me know. Because it will be difficult in just a couple of hours to revise absolutely everything, and you will have some reaction schemes to complete in the exam. So how to prepare? Well, if you look at all of the reactions and you look at the possible conversions, I think is the best way to prepare. Okay. So the key ones that I want to look at, alkane to haloalkane. Do you remember how to get to alkane to haloalkane? Can you remember the type of reaction is it? Again, do like I said before, reactant to product, what has changed? From alkane to haloalkane, we have a substitution because we got rid of a hydrogen and we have a haloalkane instead. So what is that? We use a hydrogen halide or just a halide and UV light. Okay? UV light because it's, and I want to make a note. What type of reaction is this? This is the free radical substitution. Okay. Key steps. You remember this one is the one where we have initiation, propagation, and termination step. Just to briefly revise how it works, the initiation is the one that breaks the halogen bonds. Remember UV light. We see it in this, but also in the reaction with ozone, okay, or the dangers with nitrogen oxides, okay, but the steps are always the same. So for example, chlorine, we have which type of fission causes a radical? Do you know? Say it in your mind or write it down. We have, remember, the electrons in the double bond. They evenly split to the halogens, so there is an even splitting. This is homolytic fission. Really the only mechanism where you see homolytic fission. So initiation, always formation of the radical. Propagation, the steps are always the same. So if you learn them like this, it doesn't matter which type of substitution you have. And so which type of substitution, sorry, you know what, I'm going to do like this. It doesn't matter which type of substitution, if it's the first substitution, the second substitution, or you have a weird molecule, because the steps are always the same. So we said homolytic fission to form the true radicals. Propagation, we always have the radical reacting with the the halogen. Halogen, I'm going to write the easy one, CH4. Can you guess the product? Can you write it down, the products of this propagation? But the steps I want you to remember are always the same. The chlorine takes the hydrogen, always. Knowing that, you can work out whatever it's left. So that's why it doesn't matter which substrate you have, because the first step, always the chlorine takes the hydrogen. So you have HCl, and then you're left with CH3, and the radical will be on the carbon. Then, second step, the key thing to remember is that you always have the initial molecule reacting. Okay? If you remember, radical takes forms HCl always. And in the second propagation step is always the halogen that reacts, then you can kind of fill up the gaps. Okay? In fact, would be the intermediate radical reacting, CH3. And guess what it forms? Well, it would form the desired product, which is CH3Cl, and you reform the Cl radical. So this is also important to remember that the chlorine radical is reformed. It's a catalyst. For AQA, this could be relevant because the rate topic is in it, so reaction mechanisms, but this is actually similar to designing, the multiple steps mechanisms. So this is your intermediate because it's formed and then it's used up straight away. And this is your catalyst because it's reformed at the end. Okay. Termination step, you have different options. Can you try to write a termination step for desired product and side product? Looking at this, a simple one. So desired and side product. One moment to try. I didn't tell you what the desired product is, but what reaction it say is free radical substitution. Always use logic, okay, when you need to fill reaction schemes or write products. It's a free radical substitution. We want to get the halogen, but it's a termination step, which means that two radicals bind together. So we would have the radicals that would form the desired product. So the carbon radical and the chlorine radical. And this is your first substitution. Side products could be, remember, radicals in the termination, they would react together. So the key thing is those radicals, could be anything reacting together. So you could reform the chlorine, but that's not really a side product. The side product could be the CH3 reacting with the other CH3, and guess what it forms? C2H6, completely different molecule, okay? Then remember the side product could be everything. If you have to write propagation steps of side products, can you guess what could be? This one reacting with this one, and the reaction would follow. The thing that I want you to remember is the steps doesn't, because it can get a bit more difficult. Imagine you're asked a second substitution or a more complex molecule like C2H6 reacting, or you could even have a different functional group, C2H5C, C2H5COH. You have carboxylic acid. How does that work? It's always the same. Chlorine takes the hydrogen from the hydrocarbon, if you have a hydrocarbon, or whatever, from the carbon hydrogen, HCl, and the radical reforms. Everything else you can fill it out later. Okay. So these are the key steps for the free radical substitution. I've got a request about revising it, so I hope that makes sense. If it's not clear, otherwise I prepared like many exam questions that you could also practice later today and apply these explanations. So let me see, can I clear this up? I will clear this up. Okay. Even too fast, too slow, please let me know. If you want to complain, just text me privately. If not, and you're happy, I'm happy to. Free radical substitution. Let's follow the red arrow. From haloalkane, we go to nitro, alkyl, amine. Can you guess which type of, well, reaction key, okay, substitution is written there, but which type of substitution is that? From haloalkane to nitro, amine, and alkyl. And how do you work that out? Logic, basics of mechanism, the most important thing. If you don't remember it, that's okay. During the exam, very often we forget things. We have blackouts. Logic, if you use logic, it's better. Haloalkanes, where R, it's any carbon groups, doesn't matter what. Delta positive, delta negative, always work out first the dipoles. So this is delta positive is our electrophilic center, because electrophile, electron paired acceptor, slightly positive, actual positive charge, electron poor. Okay, so this means that it would react with a nucleophile. So is the nucleophile reacting in this? So all of these would be nucleophilic substitutions. Okay. So nucleophilic substitution, haloalkanes. So it might be a bit small, but to get the ammonia, we would have the amine, primary amine, we would have ammonia. Normally it's concentrated ammonia because you want to prevent further substitution. Okay. For the nitrile, it would be potassium nitrile, okay, or potassium cyanide also called, in ethanolic solution under reflux. Okay, we don't normally use HCN. Any idea why? So sorry, I know I'm covering a lot of things, but I want, like, this could be all of the, 2-mark question, like suggest why, explain why, following a mechanism. So sorry, I've deleted the thing. Okay, I want to make a little bit of space. Sorry, I hope it's not too colorful and you can follow me, because I'm getting lost too. Okay, the one that I want to highlight, the nitrite. Potassium nitrile is used instead of HCN. Do you remember why? Can you guess why? Take 30 seconds to think about it. And this is all basic knowledge of chemistry. What are we talking about? Ionic compound, what is that? A salt. HCN, what is that? An acid. HCN would partially dissociate. KCN completely dissociates. So guess what? It would make a kind of a stronger nucleophile because it completely dissociates. Okay? So that's why KCN is used. Amine. What can we discuss about the amine? So I'm looking at the conversion haloalkane to amine. What can we discuss? Well, excess ammonia is used. Concentrated ammonia or excess. Why it's used? Well, because it depends on which product you want. Do you remember the mechanism? Can you try to sketch it out? Let's say we have this, chlorine and ammonia. Can you take 30 seconds to write the curly arrows down? Go for it. I know it's simple. It's just a nucleophilic substitutions, but why do I want you to draw the curly arrows? Because, well, first of all, remember, you have to do the drawing effort to learn organic chemistry mechanisms. That's the only way. Okay, drawing out over and over again until you are you fully understand. And then the basic of the mechanism, as I said, is the most important thing: nucleophile, electrophile, lone pairs, and so on. Mechanism relatively simple. It's one step. The important thing is that you always think about, is there a charged intermediate or not? Okay, always think about the consequences of this error, because, for example, for the case of the ammonia, sorry, there is a plus charge, okay, because it's giving kind of away this lone pair of electrons. So dative covalent bonds would cause positive charge, okay, but this adds one step in the mechanism. That's why I always want you to try to work it out with logic and not through memory, okay? So donates a lone pair, forms positive charge, chlorine is gone and it has a negative charge. Also, always thinks about everything is always balanced in chemistry. This is all neutral, the reactant side. Also, our intermediate must be neutral. So if you have chlorine that has become negative because it has gained electrons, 1 electron from the covalent bond of the carbon, then there must be the positive charge. So always keep in mind the balanced charges, okay? And then if you have that there, you can easily work out the next step of the mechanism. We give back the arrows to the nitrogen. And then you have the final product. Primary amine. Why do we have excess ammonia? Otherwise, it still has lone pair. It can just react further. So tricky questions could be that could throw you off, even though they're exactly the same mechanism. If instead of this, you're asked, you have maybe this molecule, and then you're asked to draw further substitutions. Okay, so that's where you need to think about it. But do always the same analysis: lone pairs, nucleophile, electrophile. Okay, so the amine can react further, of course, with the this, still the same mechanism, okay? It would form. Clear it up a bit. Okay, can you guess can you try on your paper to draw the consequence of this step? And then I will draw it here, but please do the effort to write down. It's really, really, really important that you do the writing practice. That's the one into the board, so please write. So when you have complex molecules coming together, I would always, like, for example, this one, I would keep it exactly written the same as it is. And then you think about, okay, how did I put the other molecule together? Okay, well, this one is gone here. Or also you can think about the curly arrow means new bond that formed. So this is this. And then what else did you have attached to the nitrogen? You still have the same. And then what else do you have? 1, 2, 3, 4, the other bute chain. Again, always keep in mind, are there any charges? Yes, there are. Also because you know that you removed the chlorine and that's negative. Once again, same steps. And this can continue. Third substitution until you get the ammonium ion. Okay. But this is a simple mechanism that can be complex in an exam if you're asked things like this, further substitutions. Do you understand? Do you want me to show you the third substitution and so on? Or is it all clear? If not, write in the chat. Otherwise, take a breath and we move on.
How come the bit that's been added on that had the chlorine on there has 5 carbons, or is it 1? Oh, so it's
4.
4. Okay.
Yeah, very common. This is super easy to get confused. Okay, it's actually, thanks for mentioning it, because the things that we think are super obvious in the exam are the things that makes you feel a bit uncomfortable, like this. Remembering that counting the carbons right. Yeah, so I want you to notice this thing. So thanks for that, because this is a very common thing to somehow get anxious about or get confused if there is this high energy thing, you know, during the exam. Always 1, 2, 3, 4. So 4. Because this is the connection with the atom, okay, not the carbon. Easy to get confused. So when you needed to draw, for example, the naming, keep that in mind as well. Okay, don't get confused. Is something that it's easy distraction error. So if you know that this could be an easy distraction error, I think you can prevent it. So in writing down skills or formulas or naming, keep that in mind and know that this is just think about it is the covalent bond between what? So covalent bond between carbons, covalent bond, carbon, nitrogen. Okay, so let's think it this way. Okay.
Also, is there another product that's being formed, HCl?
Absolutely.
Being removed.
Good.
Okay.
Exactly. So always think about what's the side product. Okay. Sorry, I hope the alarm, not sure what's happening, but there is an alarm going on. Side product, always important, because in the mechanism, maybe you can just leave it, but if you have to write this structural formula, so the actual equation, you need to notice that. So always think about what has been removed, what is the side product. So HCl is the one in this reaction. Okay.
Can I double check one more thing? Sorry.
Yes, go ahead, please.
With the Cl minus, is the curly arrow going to the hydrogen, and then from the bond to the nitrogen? How come it's not going to the positive on the nitrogen?
Okay, if it went to the positive with the nitrogen, the nitrogen would have too many bonds. So we always need to think about how many bonds does this atom want to have. Okay, so we know that nitrogen wants to have maximum of 3 bonds to be neutral. Okay, that's why it cannot form an extra bond. Okay, instead it wants to have 3 bonds and the lone pair. Okay, that's why keep an eye on the periodic table, because like this, you know, okay, nitrogen, 5 electrons, outer shell, 3 bonds. Okay, because also for oxygen, that's very common. Oxygen wants to have 2 bonds and 2 lone pairs. You know that from the basics of the, you know, the atomic structure. And that's how you know that they won't react together. So whenever you think about the combination of curly arrows, keep these things in mind. Okay, hope that clarifies. And then, yeah, please, there is nothing obvious. Okay, and if it's obvious for me, it's not obvious for you. So just make me notice this leap. So thank you for that. And then curly arrows, remember that they're quite picky about them. So when we do benzene, we will look exactly at the curly arrows, but always from either the lone pair, yeah, or the charge, and then from the bond. So always really think it as movement of pair of electrons, okay? So that like that, you know exactly where they move from. Okay, I will move on. So the others, okay, I'm sorry, I think I hope it's not too tiring for you, because I know there are a lot of mechanisms. So please, if it's too much, tell me and we go into exam practice, but I think this would be nice to revise everything. Okay, but if it's too much, please tell me. Okay. Then, well, the mechanism for nitrile and with hydroxide are exactly the same. Okay, remember, if you know the general steps, doesn't matter which nucleophile electrophile you have. Okay, with the nitrile, I want you to notice that the 2 very important conversions, which are these ones. Sorry, it's a bit weird deleting stuff, but the key ones from nitrile. Nitrile is a really nice intermediate because it can be hydrolyzed to a carboxylic acid, so that's with just addition of water on the reflux, or can be reduced to an amine. Okay, in fact, this is one of the ways to increase the length of the carbon chain. Okay, so this is the conversion to remember. And then you can also work it out. Come on, if you have a conversion, nitrile to carboxylic acid, think about it. What has happened? Well, you have OH, like OH. How did you add OH? That's probably water. So it's hydration. Okay. And amine, well, you have carbon and nitrogen now with more hydrogen. How did that happen? You know, that's addition of hydrogen. What is that? Reduction. Okay. So that's important conversion. Now, and that's the whole part of the nucleophilic substitutions, okay? The other ones that I would like to notice a little bit. Well, we've discussed alcohol, aldehydes, alcohols to ketone. I don't want to discuss that anymore. Just remember classifications, primary, secondary, tertiary are fundamental for that, okay? But one that I want to look at is the carboxylic acid part, because the carboxylic acid conversion are really important, because it's not the most reactive thing, which means that it can be converted into ethyl chloride or acid anhydride to make it more reactive, okay? So carboxylic acid to ethyl chloride, it's using I hope you can see there, it's really small. Let me zoom in. So carboxylic acid to, and follow the arrow, the red one, to ethyl chloride. We have chlorinating agents, normally PCl3, PCl5, easy one to remember, to make it ethyl chloride. Why is ethyl chloride so useful? Well, because it's a lot more reactive than carboxylic acid and can be converted into an ester or an amide. Okay? I hope you can see that. And now that's the other mechanism that I want us to do. So let me clear up as much as I can. Okay, ethyl chloride to amine, to amide. So of course, as you can see, we have, if it's a substituted amide, it would be like an amine, like secondary or tertiary amine. Otherwise, ammonia to make a primary amide. Yeah, notice the difference. Amide, remember, carbon ion. Yeah, acyl chloride. So how does that work? Let's do the mechanism with the chloride and with ammonia. Can you try to get the mechanism from this acyl chloride to the primary amide? Take a minute to actually write it down, and then can you also tell me which mechanism is that? Remember the basics. A nucleophile, electrophile must be the first thing you always do. And like, if you get confused about that, like, oh, but also the hydrogen can be delta positive and the chlorine is delta negative. Yes, but how are they going to react together? Okay, think about logically, like, what's the most possible thing that can happen? Plus, always keep an eye on the final product. That tells you what is like the bonds that have to be formed, in which position, and so on. Okay, so NH3 to the carbon delta positive, the weakest bond always breaks, which is the pi bond, and then we have an intermediate. Remember, always think about the consequences of your curly arrows. This is new bond, this is broken. Where have the electrons gone? Nitrogen now have 4 things around that's positive, okay? So notice the overall compound at the beginning is neutral. The intermediate must also be neutral. So there is a positive and a negative, okay? Then this doesn't work. We want to get the amide at the end. Always keep an eye on the final product, so you know what you need to get rid of after. With the chlorine. So carbonyl reformed, and now we have it. Remember then, each step, think about the consequence of your step. Don't go for memory. Yeah, always think about the consequence, because this would tell you that, okay, the next step is going to be like before. Okay, so you have your product as the primary amide, and HCl, your side product. Okay, name of the mechanism, do you remember it? Is addition elimination, okay? Because it's not exactly nucleophilic substitution, because it's different steps. That's why we distinguish it. But addition, elimination. Okay. And this addition elimination is the same for the interconversion of carboxylic acids. So carboxylic acid to acyl chloride, same. Acyl chloride to ester. Carboxylic acid, no, acid anhydride to ester reacting with alcohols. Okay, all of these are the same. Then the last mechanism that I want to look like this, actually there's one more, is one second. Aldehydes to alcohol. Okay, because this one, of course, is a reduction. Okay, remember the reagents. For reducing agents are sodium boron hydride, and probably it's too small, so I'm going to write it. Aldehyde and ketones to alcohol. Of course, this would form primary, secondary alcohols. Remember, sodium boron hydride. While from carboxylic acid directly to alcohol, so from carboxylic acid directly to alcohol is lithium aluminium hydride. Okay, This is explosive, like really reactive, so it's used just if like something very reactive is required. I want to highlight this one because the mechanism is the typical for aldehydes and ketones. Okay, so let's take a ketone. Reducing agent, what it does, it releases this hydride ion. Can you guess the mechanism? Can you try to write down this mechanism and guess? Well, we get an alcohol because it's highlighted there. Mechanism of this one. Try in your paper following the logic of the curly arrows. Slightly different than before because now there is no leaving group, okay? In the addition elimination mechanism, you have one element that you can remove because it's relatively stable on its own, yeah? But in this case, not, because the carbon double bond won't reform in favor of forming a, or remove, like breaking a carbon-carbon bond. So instead, this steps always requires acid after, yeah, because of this would cause would form the alcohol. Okay. So in this topic particular, very important, you would well, this is any nucleophile, which means that, well, this is a reduction one, but imagine that you had any nucleophile. This is when the topic of optical isomers is linked in, okay? Because if you have a nucleophile and you have an asymmetric ketone or an aldehyde, you would form a chiral carbon, 4 different carbons, okay? And the reason why you have an optical isomer is the shape. Do you remember the shape of an aldehyde? Shape and angle. It's planar. If it's planar, means that the nucleophilic attack from above or below this plane has equal chances. So you would form, let's say this looks like this. If you had a nucleophile, the consequence of this would be, you still have the same mechanism, right? So you form an alcohol, but you would have OH, this, and the nucleophile, chiral carbon. Okay, so be confident in writing tetrahedral structures, writing mirror images, okay? But you've practiced that plenty with the paper one, okay? Mirror images. Important thing, what's the consequence of this equal chance of attack top up from above below the plane? Racemic mixture, okay? Racemic mixture means that 50-50 or 1-to-1 ratio, the two different isomers called enantiomers, which means that the mixture is not optically active because the optical activity cancels out. Okay. Okay, the last thing to remember, I would say alkene to alcohol and alcohol to alkene, remember, is actually the same reagent, alkene to alcohol, hydration, alcohol to alkene, dehydration, uses concentrated sulfuric acid or concentrated phosphoric acid, addition and elimination. This is one somehow it's difficult to remember because it's just acid. Okay, so I'll put this worksheet on. What I would suggest you to do is, for your own practice later, complete this synthetic routes, thinking about alkane to haloalkane, and then you can think, okay, What is the condition? What is the reagent that I can write down? Can I remember the mechanism? This is a really nice comprehensive practice, okay? Alkene to alkane, and then, well, it can be any, like just make up a reagent, could be chlorine, bromine, whatever you want. Halocane to alcohol, to a primary alcohol. Write it down on the side, right? It's a nice practice to do it. Follow each error, and then on a side paper, write the mechanism, the name of the mechanism, okay? So if you want to do a nice practice, do this, okay? Complete the synthetic routes, looking at one conversion at a time. You can also think, okay, I want to go from an alkene to an haloalkane. How do I do that? Alkene to alkane, alkane to haloalkane, yeah? Or I can just go directly, okay? That's what I want you to try to notice. So this is, yeah, you can use this one with the synthetic routes here on the side in case you want to remember the reagents, okay? This is a super nice summary. Let's take a moment, because this one, I wanted to do some exam practice, but I think it's actually more beneficial to revise all of them here. Benzene, okay, a topic that comes up always. Important things to remember for it. Of course, the evidences of the aromatic structure, okay? Why is it more stable? So the evidences, and sometimes you have to do little calculations or some discussion around it, and that is the extra stability, so the enthalpy of hydrogenation being different, the fact that each carbon has the same angle, and carbon-carbon bonds, they have the same bond length, which is in between single and double bond, okay? So those are, and the fact that it doesn't react with electrophilic addition like an alkene. Those are the main evidences of the aromatic compounds. So we've seen before this mechanism, this one, we didn't see the mechanism, okay? But we mentioned already that benzene is a nucleophile. It does electrophilic substitution. What it would be nice if you practice writing the catalyst, the formation of the electrophile. So can we take this one? Can you try to write the formation of the electrophile for the reaction highlighted? Write on your paper, and in 1 minute I will write that too. So we have formation of the electrophile for this reaction. And why I want you to write this down? Because it doesn't matter if you have acylation, alkylation, or just halogenation, the formation is always the same, because this is an halogen carrier. It would pick up one halogen to form this intermediate with a negative charge, leaving behind that one with a positive charge. Remember, charges are always balanced. So the whole reactant is neutral. The product will be neutral too. So we will have CH3CO+. That's your electrophile. And then, well, where is the positive charge? You know it's from the carbon, because you also know the product. Okay? So for revision of this one, similar type of revision that I would suggest you to do. Look, you have the empty flow chart here, which you could play around with. Really, really useful. Okay. Then the important conversions to think, well, for phenol, the directing groups are really important, but also one more thing I wanted to say, okay, is this conversion. Very common flow chart to get this one. So from benzene to nitro, we have nitration. We see before the acid-base reaction with the two concentrated acids. But very important, you cannot add the amine directly to the benzene. Why can't you add the amine directly to the benzene? Can you ask, can you think about why? It's because an amine is a nucleophile, benzene is also a nucleophile, so they won't react together. I hope you're making a note of these key points that I'm saying, because all of these are exam questions that could be a couple of marks. Explain why, yeah? So first to make a note, I don't ask them randomly, okay? So what type of reaction is this, by the way? NO2 to NH2 is a, say to yourself, reduction, because addition of hydrogen. And the reducing agent is a tin with hydrochloric acid. Looking at this reaction, which type of directing group is NH2? Can you say it to yourself? It has a lone pair, as we know always. Yeah. As soon as we see an amine, we could write that down. Yeah, it directs 2, 4, and 6. So it's an electron donating group. Where is the catalyst? Why there is no catalyst here? It doesn't need the catalyst, aluminum bromide, iron bromide, because the electron density on the benzene ring is higher. Okay, higher electron density means means that it's a stronger nucleophile, so it doesn't require the catalyst. Okay. Good. And this one I will give it to you for you to practice. Okay. Phenol, similar to, well, it's this, notice same directing group as amine, again for the same reason, electron donating group. Remember that it can form a salt. What type of reaction is this? Or what reactant would cause this? Can you tell me? If we have OH to form a salt, it's actually a little bit acidic. Acidic. Okay, because it can form salt. So remember, phenol can lose the H plus, forming a salt, so it can react with a base. Okay, just very strong ones though, because it's still not a very strong acid, very strong acid. Okay, good. So this is for the flowchart to practice later. Okay. Okay, let's take a couple of minutes break to take a breath. Do you have any particular question about the mechanisms? I know I've covered a lot, but I hope this was helpful to revise the mechanisms and to prepare for flowcharts and organic synthesis. Let's take a minute and think if you have any questions looking at these flowcharts. Okay, I think I've shown you a nice way to prepare for organic synthesis, okay, so we don't have to stick to just practice past paper questions or exam questions. We can do this type of active recall. Okay, organic analysis, I think, is the second challenging part. So for organic analysis, and the hardest thing will be combining techniques, and I'm going to read a little bit the slide. So combined techniques, normally a single spectroscopic technique tells you a bit of information of the structure of a molecule or compound, but combining techniques gives you a lot of different bits, and we can use to determine the structure of a molecule or compound. So important thing, you may have very big open question, maybe we will try one today. Very challenging, and you have no idea where to start. Well, you start by thinking about the basics that you know. What do you know about mass spectroscopy? Wow, this is a big error. I've copied this from somewhere. It's spectrometry. Yeah, actually, why is it spectrometry and not spectroscopy? You see, that's why I should draw things myself and not copy them down. It's a spectrometry. Why? And not spectroscopy. Do you know the difference? Meter measures something, the actual mass of atoms or fragments of compounds. Spectroscopy is the interaction between electromagnetic radiations with matter. So infrared remember infrared radiations. And actually, if you get the chance to revise it a little bit how this instrument works, it's useful. You never know which question you may get, yeah, because it could ask NMR, which type of waves does it use? It uses radio waves. These interact with the nuclei and it causes them to absorb energy and spin. Yeah. Infrared spectroscopy, of course, it uses infrared. Infrared causes a vibration of different type of bonds. Okay, so this means that mass spectrometry, because it measures something, the mass, the key information we can get is the molecular ion. Remember, molecular ion is written like this. You can only measure ions because they have to be deflected in the magnetic field, and this tells us the MR of the compound. This is useful in the combined techniques because we normally have composition analysis to get the empirical formula, then we can get the MR from this, and therefore we can get molecular formula. So that should be your first step. We can get a little bit of structural information, but very limited, because at the end, some fragments can be different parts of the molecule, but some things can be helpful, okay? For example, if you have let me think a moment. So we have propanol and propanol, functional group isomers. We can actually use mass spectrometer to, maybe, yeah, we could use the mass spectrometer to identify which one is, but again, it's a bit limited, so if we can use the NMR, better. But for example, you could think about fragments that are only present in one molecule. For example, the CHO, it's only present in aldehyde. So if you look at the fragment corresponding for CHO, and because remember that if you have one fragment, I mean, if you split about a molecule, you end up with two fragments. So find both of them in the mass spectrometer. So if you split this molecule here, you end up having two fragments. These two fragments would be very different from the ketone one. So you know that you can identify which one is. Okay, so that's the type of structural information with mass spectrometry, but of course it's a bit limited. But most important thing, MR. Okay, infrared. What can you get from infrared? The functional group. Okay, functional group. I think the best way is like, you're familiar with the shapes of some key peaks. Okay, so you don't even need to rely on the data sheet. The data sheet sometimes can be a bit confusing since there are so many numbers and things. But if you like, there are some key shapes like carbon double bond. We know it, 1700, super sharp. OH, it's very broad peak, but OH of a alkyl is very broad and towards 3500. While of a carboxylic acid, it's closer to 3000. It merges with the peaks of the carbon hydrogen, which are these ones are 3000. So it looks like spiky instead. So these would look like this for the carboxylic acid. So knowing this can help you finding identify the functional group like that, okay? Without relying too much on the data sheet. If you have a peak, for example, here in the middle, then okay, look at the data sheet that tells you which functional group you may have. And NMR spectroscopy. Carbon and proton. Always keep in mind which one you're doing because it's easy to get confused about the environment otherwise. Carbon NMR, number, type of carbon environment. Proton NMR, number, type of protons, environment in which the protons are in. So, carbon NMR. It's a lot. This one is type of hydrogen, of course, because we have the splitting pattern. Splitting pattern tells us information about the neighboring hydrogen. So the analysis to do and how I would do it. You're likely to get a big open question for this. So you also need to know how to write things down. So for example, for this proton NMR, we don't know the integration, but what we know is that, okay, we have one peak. This one is a chemical shift, always relative to zero, which is our reference point of TMS. because it's shifted. It basically, the chemical shape tells us how different is the proton environment from my reference, which is TMS, which is tetramethylcyanide. How different is that? The more shifted downfield is, the more different it is. Okay, so I would write it like this. If you want to make it nice and tidy, also for whoever marks your paper, that would be really nice. So the peak at 0.5, that is a triplet. I could write it like this. Maybe you even know the integration. The integration can be given like this, or you could be given in a table. And then you can say, for example, let's say this is a triplet and it corresponds to 2 hydrogen. Guess what that could be? The integration tells you the number of hydrogens. So you know that the peak that makes that is a CH2. Next to, it's a triplet, so would be next to another CH2. And then I would suggest you to highlight which proton you're referring to that's responsible. But from the splitting pattern, remember n+1, you get the neighbor. So you could do this analysis and then put everything together to get a structure. For example, let's say, next one, you have peak of 2. What if you have integration of 6? So wow, what could that be? 6 hydrogen. Also, some integration, they can only be few things you think about. Is a singlet and corresponds to 6 hydrogen. What could it be? Here I'm just going to completely assume that it's a bit shifted downfield, so it could be closer to an electronegative atom, maybe not that close, but close enough. Okay. It could be attached to an oxygen or a carbon double bond. If it's 6 hydrogens, the only integration, the only thing that it could give one environment with so many hydrogen are more methyl groups together. So what is the most likely thing to be? 2 CH3 groups attached to what? Maybe a carbon double bond. That could be yours. But I hope you understand like my logic thinking around it. Like there are some things that is like, if it's integration of 6, come on, what can it be? Only a 2 CH3 groups. Integration of 9, you would have 3 methyl groups instead. Okay, that's the type of thinking. And then you have the other one, but this one I'm just making up whichever it is. Okay. I hope that makes sense. So I think now, after all this explanation, we could actually try one of this. So, but I'll let you choose. So in this paper, you have questions about practicals. Try at least one, I would suggest you, so that you can, because normally you have big open questions like 6 markers. So I would suggest you to try at least one. Try one question on chemical tests. Okay, maybe trying to remember the test that you need to know. Okay, thinking about what I said before, like some conversion and functional groups, they actually give you some observation that you can use to distinguish between functional groups. Then I would suggest you to try different flowcharts like this, but maybe trying different conversions like we did before with the big flowchart. One very nice one, it's about amino acids. This question, I think it's really nice because with amino acids, there are, well, apart from all of their activity, but also you could have a bit of calculation. The chromatography practical, it's in this one with amino acid. Plus amino acid, they're really nice because it links with acid and base topics. So you need to remember things like pH of isoelectric point, sweeter ions, okay? Think about basics of proton donor, proton acceptor when you deal with this. And then this can be linked to reactivity of amine, reactivity to carboxylic acid, could even be reactivity of alcohols, and could be linked to condensation reactions, so forming polymers. So amino acids, super nice topic to practice, to combine a lot of different functional groups together. And here you have plenty of practice to do. Again, I put another practical, and then we have some structure determinations. Okay, so with a lot of chemical tests. So here you have plenty to try. I've selected the one that seems a bit challenging, and I would like to try one. This is a bit faint, so, and then you have plenty for all of the mechanisms that you can attempt, okay? The one that I like to try is this one, because it's 9 marks, okay? And all total of 12 marks for structure determination. So, but this time I would like you to give it a go, because it's important that you actually try to, you know, to apply logic to, you know, to how you work things out. That's why I think I won't do too much of exam practice, but this is the one that I would like you to try. Okay, so give me one moment. I will set up the screen, and it's just because, remember that we want to avoid illusion of competence. So even if you feel like super confident with something, if you don't do the effort of writing things down, it still may not be, you know, enough, whatever, you know. Okay, so data sheet in a second, but 10 minutes for this, your own trial, applying everything that I said so far. Okay, good luck. So I made a few notes here, because these questions, I think it's unlikely to get a 9 marks, but just it could still be the final 6-mark question. The key steps are always have very clear the molecular formula first. Okay, so you have an idea of the size of the molecule, the atoms that are present, because that gives you already an idea of the functional groups that could be present. Second, identify the functional group. So you do that with the infrared and chemical tests. So the infrared, we can clearly see, and that's something that, of course, you would write it down. If you have to write it down, like to get the marks, you would say, well, from the infrared, there is a peak at 3,400 centimeters minus 1, and we can say that is equal to the OH peak. Okay, OH vibration, OH peak. Okay, then we can say the other considerations could be, well, there is no carbon, there is no peak at 1,700 centimeters minus 1, so it's not aldehyde or ketone or carboxylic acid. Okay, in your discussion, you could also do exclusions of other functional groups. Okay, in this one particular, because it's such an open question. Okay, so that's for the infrared. There is also another bond, I don't know if you noticed, around 1,000, and that's when the data sheet can be useful, because I know it's the fingerprint region, but when there is such a big peak in around 1,000, this is the carbon oxygen, okay? And that could be useful because it's not an ester, but if it's an ester, we would also have that carbon oxygen, okay? But that's not enough, okay, because you have alcohol, okay, but you also have a test. So that's why for the functional group, notice if there are any chemical tests. Are there? Yeah, there is green solution. So it tells us that it's primary or secondary alcohol, and that would be your another mark, your third mark. Okay, so it turns green, so it's primary and secondary alcohol, or not, it's not tertiary because oxidation reaction has taken place. Okay, so this you would have already got 3 marks, or 2 or 3 marks at least. Then for the interpretation of the NMR, either you have a table given like this, or you can work this out, writing it like this, a tidy from the spectrum. And then what I would suggest you to do is, like I did before, write down what you think each of this corresponds to. I wrote this here, 1H singlet, because only one hydrogen, only one singlet would it be? This doesn't mention anything about deuterium. So maybe is that hydrogen from the alcohol. Okay. Otherwise, leave it for last, and these would you would know that, because this one is a bit unpredictable, and normally, remember, it's tested with the deuterium shake. Then triplet, 2 hydrogen. What must be? Well, notice also the chemical shape. It's 3.8. Is the most shifted one. It means that it must be attached to an oxygen. Okay, directly. And that's why you also know that there could be another functional group, because alcohol wouldn't make it shift so much. So I know there's so many things to keep in mind, but try to think about, okay, I think this is a triplet. So it's next to a CH2. It's a CH2. So we have a CH2 next to a CH2. But then it's very shifted. So first of all, if it's just a CH2, you know that it has 2 other bonds. So it must be a neighbor. And then what does it have? It can't have anything with oxygen, right? Anything with carbon and other hydrogens. So, and it's very shifted. So my only guess is oxygen. And that's how you would know. Okay. Then next one, 2 hydrogens is a triplet. Okay. What is going to be? Is going to be another CH2. And it's a triplet, so guess what? It's next to a CH2. And guess what? Maybe is the one there, because it's 1.4, is not directly attached to oxygen. Okay. Then the quite distinctive one with 6 hydrogen singlet. What could it be? Well, see, first of all, it's 1, so it's very far away from everything. 6 hydrogens, and it's a singlet. It must be 2 CH3 groups attached to a carbon that doesn't have any other, hydrogen. So how is it possible? Well, it must have 2 other R groups, and you can write them like that as R groups. And then we have this 3.2, 3 hydrogen, and it's a singlet. What must that be? It can only be a 3.2, so it's also pretty shifted. So, well, this oxygen maybe. Always keep an eye on what you drew before. This oxygen probably has another R group attached to something else, right? Because we said there is this, there could be, if it's just hydrogen from an OH, we don't have enough oxygens, we don't have enough carbon, so there's something missing. And the 3.2 must be directly attached, and we know alcohols can have 2 things attached. So this didn't make sense if it was just the alcohol group. So we could have a CH3 attached to the oxygen. And then you try to put everything together. We said we have a carbon with the OH. Okay. What could it be attached to? The only one that is missing an attachment is this CH2, which is actually the same. So, well, let's say it's an OH. Then there is probably another CH2 attached. We said that it was next to this CH2. Next to that, there is the oxygen. Next to the oxygen, there was a CH3. And then what are we missing? Oh, there is also this part with the carbon with the 2 CH3 groups. So it could be like that, attached to the, and that would be enough. And actually this could be the structure. The thing is, if you don't get to this structure, but you do this analysis, you have most of the mark. But then what you can do is, with whatever you have, guess a structure. Just, you have the functional group. You have more or less the chunks, just put them together somehow. It's easier, I think, too. Maybe like I did is a bit too difficult, but if you do, like you have, that you have CH2 with an oxygen, just try to put it together in any way that makes sense, that only corresponds to the molecular formula. And then, if you have, of course, enough time, it's the last question of the paper. If you have enough time, either the question, this one is wrong, you lose a mark, doesn't matter. But otherwise, you can do the opposite analysis, which is from the molecule you have, does that correspond to your NMR? So you're merging two types of practices. One is from the NMR, you get the big chunks, and then you either manage to put it all together and it works, or you just put whatever you can together. You have the molecular formula and the functional groups anyway. Yeah, so you do that, and then you try to check if the NMR is correct. If not, modify your molecule until you get the same as the NMR. I hope you understand my method, because I think like this, you really have the most chances to get to the end of the question, okay? Because if it's difficult, as this one, really difficult, one of the hardest one I think I've encountered, because it was the carbon-oxygen bond, was a bit tricky to find. Chunks, put it together, does it correspond to your NMR? I hope it's clear. And sorry, we went a bit over time, but open for questions now. And well, good luck for paper 2.